Hello again. This video is the second and last video on the section on dimension and rank. This video is actually going to cover something in that section called coordinate systems. And I'm going to start by reading the first paragraph from this section. It talks about, right here, the main reason for selecting a basis for our subspace H, instead of merely a spanning set, is that each vector in H can be written in only one way, as a linear combination of the basis vectors. To see why, suppose B is B1 through BP is a basis for H. And suppose X is in H, so X can be generated in two different ways. Say it's C1B1 plus blah 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 to CPBP. And another way is maybe D1B1 plus dot 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 DPBP. But if you subtract X minus X, you get 0. And then you would subtract your coefficients there. And since B is linearly independent because it's a basis, the weights in 2 all must be 0 because it's equal to 0. So that is, if they're all 0, each Cj better equal Dj for all the j's between I and P, which shows that the two representations are actually the same. So you can generalize this or formalize this with the following theorem. So if you let H be a subspace of Rn and let beta be B1 all the way through BP be a basis for H, for every vector X in H, there is exactly one way to write X as a linear combination of the basis vectors in beta, and it is X is equal to that first way. So you had another way, they would be the same. Which brings us to the following definition. Suppose that, again, beta is B1 through BP, just as above, is a basis for a subspace H. For each X in H, the coordinates of X relative to the basis B are the weights C1 through CP, such that we have this linear combination and the vector in RP, so this is what they denoted, brackets with an X with a beta to let you know what the basis is, and these are the weights. This is called the coordinate vector of X relative to beta, or sometimes it's called the B coordinate vector of X. And there's a little note in the book. Number 1, it says it's important that the elements of beta are numbered because the entries in this coordinate vector of X relative to B depends on the order of the vectors in B. So let's look at example 1. Example 1 says let V1 and V2 be the following vectors and X be the vector 3, 12, 7. And the basis is going to be V1 and V2. So then B is the basis for H, and H is going to be the span of V1 and V2 because V1 and V2 are linearly independent. Determine if X is in H. And if it is, find the coordinate vector of X relative to beta, relative to the basis. So first we want to determine if X is in H. So if X is in H, then the linear combination of C1V1 plus C2V2 better equal X would equal X. That equation would be consistent. So let's go ahead and write down what that is. So we would have C1, and I just wrote down the V1 here, plus C2, I wrote V2 here, and the X. And that equation can be written as a matrix And to solve this matrix, this would be the C1 and this would be the C2. To solve this matrix, I can row reduce it to echelon form. I think I'm going to first interchange 1 with 3. Or maybe not. Maybe I should just divide by 3 because I'm going to end up with fractions anyway. So 1, negative 1/3, and 1, dividing the first row by 3. And then I'm going to get my zeros. Multiply the first row by negative 6 and adding to the second row to 0, 2 plus 0, and negative 6 plus 12. And then I'm going to do the same thing, but with negative 2. Add negative 2 times the first row, add it to the third row, and I should get 0. 5/3, so what is that? How did I get the 5/3? It was 2/3 plus 1, which is 1 2/3, or 5/3. And then finally, negative 2 plus 5 is 7. So we could erase this. Now I'm going to get a 1 here. I think that would be, or at least multiply everything by 3. Let's just multiply by 3. I guess I could get a 1 here. That would be good. Let's divide everything by 2 in the first one, and then multiply the third by 3. I can write down what I did. So I just took row 2 and divided by 2, put it back into row 2, and then I took row 3, multiplied by 3, just to get rid of the fraction, and put back in row 3. You can see here we're going to actually get a row of zeros now, aren't we? Because I'm going to multiply the second row by negative 5, added to the third row. So it'll be 0, 0, and another 0. So there it is. We could go a little bit further, or we could stop here. We know that x1, xc2, we know is 3. And I can find out my C2 by just plugging in a 3 there. Or I could row reduce echelon form. Let's just make that a 3. That looks nice and easy. So it looks like C1 minus 1 equals 1, or C1 equals 2. So it is consistent. Let's make that a little smaller. Oops, so we can see it. So we know it's consistent. So therefore, x is an h. The second part is find the coordinate vector. So we need to use that definition of beta. And we know from our definition, it's just our c's in the correct order. So this one would be the C1 and then the C2. And here's a nice picture of that. So this right here looks like V2 and V1. So this right here is the vector. Actually, that's V2, 2V2, 3V2. So there's V2, negative 1, 0, 1. And then in the 3D space, V1 is right here, 3, 6, 2. It's actually this one, the blue lines. And then x, the x coordinate in that space, is 2v1 plus 3v2. So the x coordinate in that space, we know from this, is we found it was 2v1 plus 3v2. And there it is right there. That's the coordinate vector of x relative to our basis. So let's look at a practice problem. The first one actually comes from the last video. Determine the dimension of a subspace H of R3 spanned by the vectors V1, V2, and V3. And they give you a hint there to find the basis. And then 2 is what we just did. Consider the following basis for R1 and R2. For R2, if the beta coordinate vector of x is 3, 2. What is x? Going the other way around. So let's look at these solutions. You can try these first if you want. Pause before you go on and see the solutions in the book. Here's the solution for the first one. So we're going to construct A to be the matrix V1, V2, V3. So these are along the columns. So that the subspace spanned by these three vectors is the column space of A. So then we can just look at the reduced echelon form, or just echelon form, and realize that there's two pivots. And therefore, those two vectors, the first two columns of A, are the pivot columns. They form the basis. So therefore, the answer would be the basis says, determine the dimension. They didn't even ask for the basis. Never mind. So determine the dimension. So the dimension is 2. If you did want to know the basis, it would be the V1 and V2. I guess we could write that down since I started it. But that's the answer right there. And they have a picture here that's really nice. They show V1, V2, V3. They show 0. They show the column A. The dimension is 2. Here's the solution to number 2. Oops. Let me see if I can get that all on one page. So they say if the B coordinate vector of x is 3, 2, then x is formed from a linear combination of the basis using 3 and 2. So they say x is 3b1 plus 3b2, where this right here is the b1. I'll just say where this is the b1 and this is the b2, since they didn't write that down. But they did on the second line. 3, there's the b1, there's the b2. They multiply there together, you get 3 plus 0.4, 0.6 plus 2. So there is the x. That's the answer. They wanted you to find the x. The basis B1, B2 determines the coordinate system of R2, illustrated by the grid in the figure. Note how x is 3 units in the B1 direction and 2 units in the B2 direction. So there's x, here's the B1, and here's the B2, all in 2D. Right? B1 is like 1.2, and B2 is 0.21. So those are the two vectors there. And then the x is 3 of these and 2 of the B2s. And that concludes this section.